So thank you very much for arranging this event and for the opportunity to speak here. And thank you all for coming. Can you hear me properly? Okay, very good. Okay, so I'm used to thinking of thermodynamic formalism as a tool for studying dynamical systems with many different invariant measures. And then thermodynamic formalism allows you to pick one from the multitude. But actually, in this mini course, I'm going to show you an application of some ideas of thermodynamic formalism to the study of a completely different type of dynamical system, namely the irrational rotation. And specifically, what we're going to do is we're going to talk about the phenomenon of irregularities in a uniform distribution. I should tell you that everything that is new in this talk is joined with Dmitry Dolgopyat. And there is a preprint. Okay, it's not yet on archive, but I will now show it to you that it really exists. We have been working on it for more than 10 years, and we are nearly done. Of course, I could have said that 6 years ago, but and I did, but well, I think now we really are nearly done. Okay, so let's start with just explaining what irregularities of uniform distribution is all about, and let's start with the uniform distribution. So I'd just like to remind you of Weyl's theorem. So suppose alpha is irrational and I is a subinterval. Then Weyl's theorem says that then if you count the number of times n alpha mod 1, so this is supposed to mean the fractional part. Sorry. N alpha mod 1, the number of times that this number falls inside the interval, then it's approximately equal to n times the length of the interval, and there is an error term, and the error term is little o of n, okay? As n tends to infinity. That's a uniform distribution. It's universal phenomena. It's true for all intervals and for all irrationals. Now, what is the phenomena of irregularity of uniform distribution? Well, this is the observation that when you look at the error term, perhaps you would have expected it to oscillate evenly around 0, certainly I did, but it turns out that that's not always the case. So irregularities in uniform distribution is a bias in the error term. So the error term is, I'm going to write it like this, dn alpha I. It's going to be the number of visits up to time n of this sequence to the interval minus the leading order term. It turns out that sometimes for some alpha, for some interval I, when you look at the behavior of this error term, it does not spread out evenly on both sides of 0. Now whereas this theorem is highly universal, it's true for all subintervals, for all irrationals, it's unbelievable. This is extremely non-universal, okay? I would like to stress this. This is a highly non-universal phenomena. It's sensitive to everything, okay? So this is very sensitive certainly to the value of alpha, but also to the endpoints of the interval, okay? So this is universal. This is not universal. Highly dependent on all the parameters of the problem. And because we have 3 parameters here, that's too much for me. I'm going to fix 2 of them and just play with the third. So what I'm going to do throughout this talk is I'm going to fix, because of this, I'm going to fix my interval to be always 0, 1/2, and I'm going to vary alpha and compare the behavior for different angles, okay? Now, it's certainly very, very interesting to understand what happens for other intervals, but if you fix an alpha, if you look at what happens at other intervals, you have to understand that the conditions that you're going to need on the endpoints are going to depend on alpha, okay? So these are not three independent parameters, they are dependent. And any results that you may hope to get for more general intervals would have to involve conditions on the endpoints which depend on the angle, okay? But I'm not going to do this. This is too complicated for me. I'm just going to make my life easy and fix the interval to be 0, 1/2, and then see what can be said on this quantity, which by the way is called local discrepancy, the local discrepancy function, for different alphas and the same interval. Okay, so now let's put notation here. From this point onward, I is always going to be the half interval, and dn alpha is going to be this quantity. The error term in Weyl's equidistribution theorem for this interval. You can already see one feature of the setup which makes life easy, and that is that this is always inside a discrete closed subgroup. Okay, if I had an irrational interval, then it would still be a countable collection of values, but they may be dense in generated dense subgroup. So this already is very convenient, and it's going to be important for us later. Okay, so I spoke about biased behavior. Let me now try and explain to you what I mean by this. So people have discovered various types of bias that appear here, and okay, so forms of bias. Certainly the most dramatic one, and also the first to have been discovered, is what I'm going to call in this talk a sign bias, although a much more common term for this in the literature is heaviness phenomenon. So this was, it's not clear to me who discovered it first. The earliest papers I've seen are by Vera Schoch, and there is a sort of mysterious remark in a paper by Veitch that he learned of this phenomena from Nelson Markley. And it has been studied deeply by Boschernitz and Ralston, and later I will tell you the full picture on this. I'll also put the names Boschernitz and Ralston here. And finally, I will also mention the name of Perez, who found a conceptual, rather general explanation of why this heaviness phenomena happens. So first of all, so what is sign bias? Sign bias is the observation that there exists alpha, irrational alpha, such that the error term always has the same sign for all n. So this is very strange. I mean, you have an error term, it's supposed to fluctuate around 0, but sometimes it doesn't. Sometimes it's always has the same sign. That's the most dramatic form of bias. Here is another more subtle form of bias, which I'm going to refer to as a global bias in this talk. It was first discovered by Joseph Beck quite recently, 2010. And I will give you a precise formal statement a little bit later. Now let me explain to you on a more heuristic level what he discovered. So what he observed was that there exists alpha such that the histogram of the first n terms, the first n entries in the sequence of error terms has drift. Now, what do I mean by this? So what is a histogram? So this is supposed to be How do you do? Yes. Okay. So I remind you that when you have a sequence of numbers, you can do various statistic analysis with it. And one of the first things that you can do is you can form a bar chart that has on the x-axis all the possible values. And the y-axis is the number of times that you see these values. And then you draw a bar chart. And back show that if you take quadratic irrationals, like, I don't know, square root of something, square root of n, and you draw this bar chart, that there is a scaling limit. If you look at the graph from far away, it looks like Gaussian. He showed it for quadratic irrationals. Now we know that it holds for a larger class of irrationals, but let's talk about quadratic irrationals for the moment. And when you have, so you look at this from far away, that means mathematically that you apply some scaling, and after scaling it looks like a Gaussian bell-shaped curve. And this bell-shaped curve has two characteristics. One of them is the center, the mean, and the other is the characteristic width, the square root of the variance. Okay. And he observed that for some alphas, the mean is not negligible compared to the variance. So this means that if you look at the histogram from far away, it's not centered at zero, it's shifted. So this we are going to call global bias. I'll give you a formal statement a little bit later. The third form of bias, which is actually the one we are going to focus on in this mini course, is something I'm going to call local bias. And local bias means that some possible values of Dn alpha. So Dn alpha is just a sequence. It can only take countably many values. For example, in this particular case, it can only take half integral values. So you look at the values that are attained by the local discrepancy function, and local bias is that some possible values of Dn appear more frequently than others. So basically, what you have to do is you have to look at the number of times Dn alpha is equal to one possible value, let's say 0, just an example. And let's look at the frequency that this happens, and let's compare it to the frequency that you see another value, possible value. And let's assume that eta 1 and eta 2 are such that you are not dividing by 0. Let's even assume more, that the numerator tends to infinity and the denominator tends to infinity. Well, the phenomena is that sometimes even if this tends to infinity and this tends to infinity, the limit doesn't converge to 1. Okay? So obviously I don't need the 1 over n's. It simplifies. I'm going to call this ratio R n eta 1, eta 2. Okay, so this is local bias. No. Okay, so let me be a little bit more concrete. No, I will not have here. Let me be a little bit more concrete, and let's just examine what happens to the first irrationals that I at least can think of. So let's see, let's form a table, and we have square root of 2, square root of 3, not square root of 4, okay, I need irrational, square root of 5, square root of 7, and let's compare their bias properties. Sign bias, global bias, local bias. Okay, so what happens with square root of 2? Square root of 2 is very bad. It shows all forms of bias. Square root of 3 is extremely good. It shows no form of bias. Square root of 5, what is good? No, square root of 5, yeah, of course. All forms of bias. Now, it's not periodic, okay? So square root of 7 doesn't show this. It shows this and that. It turns out that you cannot get any other configurations with quadratic irrationals, but if you move a little bit further to bounded type, then there is some number alpha naught of bounded type such that, you have this. Okay, what is bounded type? That's important. Most of these mini-course, all of these mini-course is going to focus on numbers of bounded type. So I remind you that every irrational can be expanded into a continued fraction in this form. The regular continued fraction is the one where the entries are all natural numbers. Okay, sorry, natural numbers bigger than or equal to 1, because this is France, except the first one, which could have a sign. And bounded type is also equivalent to this Diophantine property, which makes it a natural condition. So the statement is that you can construct a number of bounded type, which cannot be a quadratic irrational, for which you have this configuration. So clearly something very strange is going on. And what's the difference between square root of 2 and square root of 3 and square root of 7? Okay, and this is exactly what we are going to discuss. So what I'm going to do next is I'm going to just give you the main results on these three forms of bias. Basically, these are the characterizations of the irrationals of bounded type, for which you get sign bias, global bias, and local bias. And then the remainder of the mini-course will be an explanation of some ideas in the proof. Okay? Any questions up to this point?
So here, can you have all 8 possibilities?
Not for bounded type. Not for bounded type. What happens for general irrationals, I don't know. There are some dependencies. I mean, the sign bias obviously implies drift and local bias. So it implies drift at least. Okay, so now let's talk about characterizations. I'm going to start with of alpha with bias. And I'm going to start with the best result, which is due to Boschernitz and Ralston, and it's a characterizations of the alphas which exhibit sign bias. Okay, so theorem. Suppose alpha is any irrational. This is the only result in this mini course which does not assume bounded type. Has regular continued fraction expansion then dn alpha is always positive if and only if for all k odd, ak is even. Okay, very clean. Okay. Oh no, I can use this one. Okay, so now let's talk about global bias. So now I'm going to assume, suppose alpha is of bounded type. Okay, BT means bounded type. So the entries in the regular continued fraction expansion are bounded. Okay, and let's also assume that beta, which is 2 alpha minus 1, okay, has even continued fraction expansion, which looks like this. So I remind you that the even continued fraction expansion is another expansion of irrationals where all the entries are even. Of course, you need to sacrifice something, and what you sacrifice is positivity. Okay, so the even continued fraction expansion is when these are all even numbers, non-zero even numbers, but you have to pay a price, and the price that you pay is that maybe some of them are negative. Okay, and then they always exist. The existence of even continued fraction expansions goes all the way back to a 19th century mathematician by the name of Smith, and it was rediscovered by Schweiger. Okay, so this is the Beck's theorem for quadratic irrationals, and for general numbers of bounded type, it's due to d minus I, and for more general intervals, which I'm not going to specify, it's due to Bromberg and Ulchigrai. So they proved that there exists Vn tending to infinity in An reals, such that what? Such that the scaling limit of the histogram is Gaussian. And here is the formal statement. If you look at the number of times such that, now pay attention because all the information is going to be in the subscripts. I apologize for this. So the little n is sort of random. It runs from 1 to big N, minus a capital N. A capital N is constant. It doesn't change when little n goes to infinity, divided by square root of Vn inside AB, converges as n tends to infinity to the Gaussian weight of the interval. Okay, so basically, okay, again, so this is very important. So little n runs from 1 to capital N. D of little n, what we are counting is how many little n's there are between 1 and capital N, for which the value after this affine scaling falls inside an interval. Okay? And the result is that the frequency of these n's converge to what the Gaussian distribution predicts. And this is exactly the formal way of saying that when you draw the bar chart of the histogram of the first n values, capital N capital N values of the local discrepancy, if you look after affine scaling, it converges to the Gaussian distribution. Okay. Remember that 2mi's are the entries of the even continued fraction expansion. So now, if 1 over square root of n, j going from 1 to n, sine of the so what you have to do, you have to look at the sign changes at even places. Okay, so if this converges to 0, then a n divided by square root of v n tends to 0, and this means that there is no bias, no local bias. Okay, so you look at this histogram from far away. Well, a n is so close to 0 compared to the width that in the limit it looks as if the histogram moves to the center. Sorry, no global bias. Thank you very much. Yes, I mean no global bias. On the other hand, if this limit does not tend to 0, then a n over the square root does not tend to 0. So there is global bias. Okay? So how does this thing work? So let me show you how this works. Let's do it here. Suppose you have square root of 2. Then you look at 2 times square root of 2 minus 1 and expand it into even continued fraction expansion. There is a sort of a Gauss algorithm that is attached to this problem. So there is a way to do it. And it looks like this. So you see that at all even places you have a sign jump. Okay, so the limit is actually infinite. And this gives you bias, global bias. On the other hand, if you do it for square root of 3, then all entries are positive. So there are no sign changes at all. So this is the difference between square root of 2 and square root of 3. One of them has many sign changes in the even continued fraction expansion. The other one doesn't. That's why one behaves much better than the other. Okay? So this is characterization of global bias. And now, what about local bias? How do I do this? Just a second, I have to concentrate very now. Okay. Oh. Yes, sorry. Exactly. Yeah, exactly. So it's at the odd places, not the even places. Yeah.
Is there a connection between existence of the one limit and existence of the other limits? In number
3? Soon everything will be revealed. So yes and no. I mean, okay. So now characterization of the local bias. Let me add another notation here. Rn eta 1, eta 2 is the ratio of frequencies. Local bias. Suppose alpha is of bounded type, beta is 2 alpha minus 1, has this even continued fraction expansion. If 1 over n, there it was square root of n, now it's going to be n. Tends to 0. Then for all possible values, so in our case, these are all half integers, the frequency ratio, okay, this one, the frequency ratio converges to 1. So that's no local bias. But if two m 2j plus 1 doesn't tend to 0, then there exist two possible values such that R n does not converge to 1. So that's local bias. Now let's go to Vaughn's question. Vaughn asked if there is a relation between the two conditions. And let me tell you something. There's a result of Core, Kreikamp, and Arturo Lopez, Kreikamp, Lopez, which says that if you take a quadratic irrational, then the even continued fraction expansion is eventually periodic. You all know, okay, I'm sure you all have heard this about the regular continued fraction. So for regular continued fractions are eventually periodic if and only if the number is a quadratic irrational. That's also true for the even continued fraction expansion. And if that is the case, then when you look at this series, this is a series along a eventually periodic sequence. So either it's bounded or it goes to infinity like a linear function. And then you see that the two conditions are equivalent. Okay, if the sum grows like a constant times n, then either the constant is 0 and both criteria for no bias hold, or the sum is non-zero and both criteria fail. Okay, so for quadratic irrationals, it follows that indeed the two conditions are equivalent. But it's very, very easy to write down an even continued fraction expansion of an irrational for which one of these fails and the other one holds. Okay, so which is the stronger? This is the stronger, right? So I can violate this but satisfy this. But the opposite. It's all very confusing. You understand what I mean? Okay? Okay. Now, let's look a little bit closer into the scenario where you have local bias. So here is the theorem. Under, oh no. There exists alpha of bounded type such that there's exponential local bias. Okay, so for every xi, with parameter xi, what does this mean? It means that if you look at the ratio of frequencies, so I remind you that this fraction is the ratio of the frequency of times you get eta 1 and the frequency of time you get eta 2. So there exists an alpha for which this converges for all possible values, in our case all half integers, to the exponential of xc times eta 1 over eta 2. So not only is the limit not 1, there is exponential bias in some direction. The direction depends on whether xc is positive or negative. And here's another theorem for all alpha in beta type. The only possible limit when the limit is not 1 is of this form. So if for all eta 1, eta 2 r and eta 1, eta 2 converges to some limit, then necessarily rho eta 1, eta 2 has this exponential form. Open problem. Which rho appear for irrationals not of bounded type. I don't know. I don't know how to touch this question. Okay, so in the case of bounded type, you may have local bias because this ratio doesn't converge, it oscillates without converging. That's actually very common, we'll see later. But you may also have local bias because this ratio converges but not to 1. If that happens, it has to be an exponential. Question is, what happens if you remove the bounded type condition? That's open. Okay, so these are the results. And what we're going to do next is I'm going to translate them into problems in dynamics, specifically ergodic theory, and then we'll discuss some ideas how to analyze them. Any questions on the results? Yes?
Can you say one more time what rho is?
Yes. Imagine, okay, let's start again. So local bias is the scenario where the frequency ratios does not converge to 1. There are two ways it can fail to converge to 1. One is that it oscillates without converging. Okay? There are 3 ways actually. Another one is that it goes to 0 or infinity without being 0 or infinity along the way. The third possibility is that it converges, but it doesn't converge to 1. Now the question is, can this happen? Answer yes. In fact, for every xc in R, you can find an alpha of bounded type such that the limit is exponential. That's called exponential local bias. It turns out that with numbers of bounded type, you cannot get other limits. Okay, that's another theorem. I'm asking, suppose we remove bounded type. Can you get other limits? I don't know. Other questions?
So here you assume that the limit is finite.
Yes. 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 Thank you. That's actually important. Yes. Yeah.
How do E pi into the scheme?
I've been asking myself this question since I became a mathematician. Maybe we'll see later. Okay, so now.
Is it known what type of bias they have?
What?
Is it known what type of bias you get for E and pi?
I don't know. Yeah.
This general result that things converge to a Gaussian when you're bounded type.
Yeah.
Are there examples if you're not bounded type where you don't converge to a Gaussian?
Absolutely, absolutely. We know that if you take a typical alpha, then there is no convergence, no distributional convergence. Other questions?
So your hypothesis there was that every e1, e2, there's a ratio converges to something.
Yes.
Could it possibly be enough to get just one pair or?
Okay, that's a very good question. So we can show that if it happens for a certain bounded collection of etas, then there is a convergence for all of them, but we can't show it just for a pair. Probably it's because, not because it's false, but because we can't. Other questions? Okay, time is running short, so let's move on. I'm going to explain to you now, I can do all of them. No, I cannot. I'm going to explain to you now a couple of reductions that are well known, that reduce this sort of problems, to problems in dynamics. And the first reduction is very classical. It's due to Klaus Schmidt and Bill Veitch. And in fact, it has been extensively studied by the French school. Okay, so reduction. To dynamics. So we are going to Veitch. Klaus Schmidt. So he gets an initial because I know many Schmidts, but in fact I only know one Veitch. You can correct me if that's not the case. So what we are going to do is we are going to define the cylinder map. It's T alpha acting, it's a skew product. T alpha xt is x plus alpha modulo 1 t plus 2 times the indicator of 0, 1/2 minus 1. And what happens with this skew product, you can imagine, if you iterate this, you get the Birkhoff sums here. The Birkhoff sum of this term counts how many times you enter the interval. The Birkhoff sum of this one subtracts n, which is twice the length of the interval, and therefore we have the following basic identities. T alpha n 0, 0 is n alpha, and 2 times dn alpha. Okay, I sum, iterate the skew product here, you get the Birkhoff sum of this thing. This counts 2 times the number of visits to the half interval. This one counts 2 times the length of the interval. So this means that if you look at the ratio, the frequency ratio, then this is the ratio of 2 Birkhoff sums. And we have immediately moved to the setup of ergodic theory, because it's a matter of studying Birkhoff sums. But not almost everywhere, at a particular initial condition. So remember this. The reduction is that the problems that we have discussed translate to understanding the asymptotic behavior of ratios of Birkhoff sums for a specific initial condition. Okay? What about almost every initial condition? So let me tell you what is known. So there are some very illuminating results on the almost everywhere behavior that we need to be aware of. Ergodic theory. of T alpha. So the first result proved by Klaus Schmidt for square root of 5, I think, or maybe the golden ratio, but more generally by Kohns and Keen and Aronson and Keen. Mu 0, which is the Haar measure, is ergodic. An ergodic invariant radon measure. But it's infinite. Okay, what is radon measure? A radon measure is a measure that integrates continuous functions with compact support. So it's equivalent to say that compact sets have a finite measure, like Lebesgue measure on the real line. Okay, that's a radon measure. Big surprise for me, at least, is a theorem by Nakada that there are other invariant radon measures. Okay, or for every xi, there exists a unique ergodic invariant radon measure mu xi, which is normalized. And so that if you apply the transformation D, which I will tell you what it is in a minute, the measure is not invariant. So what is D? It's a shift on the second coordinate. This is exactly like Babiola-Dropier measures for horocycle flows. For every irrational alpha. Yeah. This is exactly like the discovery of Babiola-Dropier measures for the horocycle flow. You start with a system that is supposed to be uniquely ergodic. You look at the Z extension, and suddenly unique ergodicity is gone. It was a huge surprise, this type of results. Third result, Aronson, Nakada, Rita Solomiak, no other measures, invariant ergodic radon measures. Okay, so every ergodic invariant radon measure that is normalized by this condition is equal to mu xi for one of those x's. Okay, this should start smell to you like this theorem that if you have rho, then rho has to be exponential. You should start feeling the connection, and indeed, why is there a connection? Because clearly, if you look at the description of the frequency ratios as ratios of Birkhoff sums, clearly this is related to the question whether 0, 0 is generic in the sense that the ratio ergodic theorem holds. Okay, if you know that 0, 0 is generic for mu 0, you will get that the limit is equal to 1, because by the ratio ergodic theorem, the limit will be the measure of t times 2 eta 1 divided by the measure of 2 times t times 2 eta 2, and that's 1 for Lebesgue measure. But if the point is generic for mu xi, then the ratio of the integrals is not going to be equal to 1. It's actually going to be e to the xi times the difference of the etas. That's the connection. But of course, now that you know that the system is not uniquely ergodic, there is a third possibility, and that is that there are orbits which are not generic for any measure. That indeed happens. Okay, so this is why this measure rigidity, this is why you need to do additional work, because these measures give you pretty good understanding of what happens for almost every initial condition, but we are interested in a specific initial condition, and it is possible And indeed it happens that this specific initial condition is not generic for any of the measures. In fact, that's what happens for square root of 2.
So these measures, they are also conservative?
Yes. Yes, they're also conservative. Thank you for this comment. Okay, so this is the first reduction that I wanted to mention. Now let me mention another. Oh my God. I'm out of time. Yes, yes. What? 20 minutes? Oh. No, it's not going to work in 2 minutes. So no questions next lecture.